Hello everyone, welcome back, it's Tamás Jávor and Rubber Duck Physics again. The last video we finished with an important question. If motion affects both time and length, what does that mean for the order of events? Could two observers moving relative to each other disagree on whether two events happened at the same time? To answer this, let's look at a thought experiment that reveals something deeply strange about time itself. Imagine a train moving at very high speed, not negligible compared to the speed of light, along a straight track. The yellow duck stands on the platform, watching the train pass. Meanwhile, the blue duck sits inside the train, exactly at its midpoint. Now, just when the midpoint of the train carriage and the blue duck is aligned with the yellow duck, let's emit two flashes of light, one from the front of the train and one from the back. As you may intuitively expect if you have already accepted the second postulate of special relativity, the light signal from the front reaches the blue duck before the one from the back. On the other hand, the two beams meet exactly in front of the yellow duck. We assume that the blue duck doesn't cover up and block the way of either of the beams. The key question: did these two flashes happen at the same time? To the yellow duck on the platform, the answer is simple. Since the flashes were emitted at the same moment and traveled equal distances toward the middle, they must arrive at the same time. So the yellow duck concludes, these two flashes were emitted simultaneously. But what about the blue duck in the train? From its own perspective, the duck is not moving. Instead, the yellow duck and the train platform are moving backward. And here is something subtle, but incredibly important. The blue duck considers itself at rest. Remember, that was one of the first facts we stated about observers in reference frames. You can rewatch this in video number 1. Since all motion is relative, the blue duck does not explain the earlier arrival of the front flash by saying, I moved toward it. Instead, it concludes, the front flash must have been emitted earlier than the one at the back. This is the key idea of relativity of simultaneity. The two ducks disagree on whether the flashes happen at the same time. Now, you might be wondering, we have emphasized over and over that light always travels at the same speed for all observers. So how can we say that the blue duck caught up to one light beam coming opposite, or that the blue duck could run away from the other? The answer is that the blue duck does not see light moving faster or slower. It still measures both flashes moving at the speed of light. Instead, it explains the different arrival times by saying that the flashes were not emitted simultaneously in the first place. But how can two observers disagree on the order of events? Doesn't one of them have to be right? Here is the shocking part. Neither duck is wrong. There is no universal true answer. Simultaneity depends on motion. This is the fundamental idea. Simultaneity itself is relative. Two events that are simultaneous in one frame are not necessarily simultaneous in another. Some might think that the relativity of simultaneity is just an illusion or measurement error caused by travel times of light or information to observers in different frames. But this is not the case. Even if we accounted for all delays of information, observers in different frames would still disagree. Others studying relativity for the first time may think that one frame, maybe the stationary one, has the real timings and the real order of events, while a frame moving relative to it is just distorted, so therefore can sometimes flip the true order of events. This is also false. All inertial frames are equally valid and simultaneity is truly relative. At first, the relativity of simultaneity seems like a strange and inconvenient fact. But it turns out that while distances and time intervals are relative, there is something more fundamental than distance or time that is the same for all observers: the space-time interval. Whatever that is, for the moment, then we'll define it exactly, this is a quantity that remains unchanged even when different observers measure different distances and different times. Let's think of it like this. Imagine a grid where you mark 2 points. Different coordinate systems might describe the x and y components of the section, connecting them differently, but the total length of the section stays the same. Similarly, different observers measure different space and time values, but the space-time interval stays constant. Mathematically, the space-time interval is calculated by space-time interval squared equals bracket speed of light times time bracket back squared minus distance squared. Here we are working with distances in one dimension, the x direction, but the definition of space-time interval can be extended to include distance squared in 3 dimensions. Unlike ordinary distances, notice that we are subtracting the distance terms instead of adding them. This is what makes space-time behave so differently from normal geometry. Even though different observers measure different distances and times, the space-time interval itself stays the same for all of them. Let's apply this equation to a simple example. Suppose 2 lightning strikes happen 5 meters apart and 3 microseconds apart in one frame. Using the formula, we calculate space-time interval squared equals 3 microseconds times speed of light squared minus 5 meters squared. After the square rooting, we get the space-time interval in meters. Now, another observer moving at a different speed will measure different distances and times between the 2 strikes. But when they plug their values into this equation, the space-time interval comes out the same. Therefore, do not believe common popular quotes like "since Einstein everything is relative," especially when people want to find an excuse for something they see a bigger deal or less important than you. You can tell them that although many facts are relative, but, for example, space-time interval is invariant for all observers. We have seen that different observers measure different distances and time intervals, but they all agree on the space-time interval, just like how different coordinate systems give different x and y components for the same section in a grid, but its total length stays the same. This shows us that space and time are deeply connected, something we have seen again and again, from the Lorentz transformations to simultaneity, time dilation and length contraction. If space and time are so intertwined, could we draw a reference frame that has a time axis, resembling but not quite the same as a distance-time diagram? Could we find a way to visualize space and time as part of a single unified structure? That's exactly what we'll explore in the next video. Before we go, let me talk to you about myself as also an online tutor. If you need individual or small group help with high school physics or math studies, I am contactable at the email address you can find in the description of the Rubber Duck Physics YouTube channel. If you want to find and copy it, open the channel info in a web browser on a computer. Thank you for learning with me about relativity of simultaneity and the space-time interval, and see you in the next video.